This is a wonderful piece of ASC2 art. It is a conceptual 3D visualization of the magnitude of a system transfer function. The magnitude, or absolute value, of h evaluated at S, plotted over the complex S-plane. Here is a breakdown of what the diagram is showing and the physics behind it. 1. The terrain, the complex S-plane. The surface baseline. This represents the complex S-plane itself, where the magnitude of the transfer function is 0. The axis representing the real part of S, also called the real axis. Movement along this axis determines the damping, how fast a signal decays or grows. Left half plane, negative real part of S equals stable decays. Right half plane, positive real part of S equals unstable, grows exponentially. The imaginary part of S-axis, also called the imaginary axis. Movement along this axis determines the frequency of oscillation. The further from the real axis, the faster the oscillation. 2. The features, poles and zeros. This diagram visualizes the transfer function called h of S, which is equal to n of S divided by d of S. The peaks equals poles. The peaks marked with caret represent the poles of the system. What they are: poles are the roots of the denominator d of S. At these exact points in the S-plane, the transfer function's value goes to infinity, hence the tall peaks rising from the surface. The rule of symmetry. For physical systems with real coefficients, complex poles always come in conjugate pairs. This means if there is a peak at S equals A plus JB, there must be an identical peak at S equals A minus JB, mirrored across the real part of S-axis. The O's equals zeros. These are the roots of the numerator n of S. At these points, the transfer function's magnitude drops exactly to 0. They are pinning the fabric of your surface down to the baseline. 3. Decoding your labels, the key concepts. The labels perfectly capture the relationship between pole location and time domain behavior. Tall peak near S1, long-lived oscillation. Observation. These peaks are very tall and sharp. In the 2D plane, they would be located close to the imaginary vertical axis. The physics. Oscillation. Because they have a significant imaginary component, they are far from the real axis baseline, the system oscillates. Long-lived. Because they are close to the imaginary axis, their real part is very small. There is very little damping. The oscillation will last for a long time before fading away. Think of a tuning fork or a very bouncy spring.